Analytic geometry might be far more dangerous than you think. But how can a simple line connecting 2 points turn into one of the most powerful ideas in mathematics? Imagine a curve, any curve. On this curve, we are going to tell a story that begins with 2 points but grows into one of the most powerful ideas in mathematics. Here is our function, a simple parabola. I fix one point, x equals 1. This will be our reference point, and I place another point. For now, it is far away, at x equals 4. Look at the line connecting these 2 points. It starts exactly at the yellow point and ends exactly at the green point. This is a secant line. Now I mark 2 important distances. This horizontal distance is delta x. This vertical distance is delta y, and the ratio of these two gives us the slope, delta y divided by delta x. Right now it is about 1.1. Delta x equals 3, which means there are 3 units of distance in the x direction between the points. Delta y is about 4.3. Now, watch. I will move the green point closer to the yellow one. Pay attention to how the slope changes. Delta x gets smaller, and the slope changes as well. Even closer, the slope decreases. Now delta x is 1. Delta y is about 0.9. The slope is 0.9. We keep approaching. Delta x is now half. The slope is about 0.75. The points are extremely close now. Delta x is almost 0. A little closer, about 0.603. It is approaching a number. Do you see it? The slope is settling toward a value. Delta x is almost 0. Delta y is almost 0 as well, but their ratio approaches about 0.6, and that is the moment. The line connecting 2 points turns into a line that touches the curve at a single point. The secant line becomes a tangent line, and the slope is exactly 0.6. This number has a name. It is the derivative of this function at x equals 1. Now let us write mathematically what we just saw. As delta x approaches 0, the limit of delta y over delta x becomes dy over dx. A discrete ratio becomes a continuous one, and that is the formal definition of the derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. What you just saw with your eyes is exactly what this formula describes. The average rate of change between 2 points becomes the instantaneous rate of change at a single point. Now let us go one step further. Here is another function, a beautiful curve with peaks and valleys, and I add a second axis below it. On this axis, we will build the derivative function not from a ready-made formula, but from what we see. This yellow point will move along the curve, and the small line next to it is the tangent at that point. We track the slope of that tangent in real time. Right now, the slope is positive. That means the function is increasing. On the lower graph, I mark this slope as a point. As the tangent moves, this point will leave a trace. Watch carefully. The tangent slides along the curve. The slope starts positive, then the tangent becomes horizontal and the slope drops to 0. What does that mean? The function stops increasing. Now the slope becomes negative. The tangent tilts downward. The function decreases. It approaches 0 again, becomes horizontal once more, and turns positive again. The function starts increasing again. And now the trace is complete. Look at the graph below. That trace is actually the derivative function itself. And when I draw the real derivative graph, look, it matches perfectly. Notice something very important. The points where the derivative is 0 correspond exactly to the peaks and valleys of the original function. Do you see the connection? When the derivative is 0, the function changes direction. F prime equals 0. The tangent is horizontal. The function is neither increasing nor decreasing. It is a turning point. Where the derivative is positive, the function increases. Where the derivative is negative, the function decreases. The derivative is like an X-ray of a function. It reveals everything happening inside it. Now let us look at the rules of differentiation. X to the power of 1, a linear function. Its derivative is constant, 1. The slope is the same everywhere. Now n equals 2. We see x squared. Its derivative is 2x, which is a linear function. The slope increases as x grows. N equals 3. X cubed appears, and its derivative is 3x squared, a parabola. And n equals 4. Do you see the pattern? Each time the exponent comes down and decreases by 1. This is the power rule. The derivative of x to the n equals n times x to the power of n minus 1. Bring the exponent down and subtract 1. That's all. Now consider the product of two functions. The green function is f. The red function is g, and the purple one is their product. Notice how the product reflects the combined behavior of both functions. But how do we differentiate it? This is the product rule. The derivative of f times g equals f prime times g plus f times g prime. Differentiate the first and multiply by the second, then keep the first and differentiate the second and add them. That's the derivative of f times g. And now the most powerful rule, the chain rule. Functions inside functions. We see x squared, and the purple graph shows sine of x squared. One function is placed inside another. The chain rule says differentiate the outer function while keeping the inner function unchanged, then multiply by the derivative of the inner function. The derivative of sine is cosine. The inner x squared stays as it is. Then multiply by 2x, the derivative of x squared. The result is cosine of x squared times 2x. Now look at this function. Peaks, valleys, twists, and turns. We will reveal its secrets using the derivative. We slide the tangent line along the curve. Positive slope, the function climbs. The slope decreases, the climb slows. It stops. The slope is exactly 0. The tangent is horizontal. This is a peak. Then it becomes negative. The function descends. 0 again, a valley, and another one. The slope is 0 again. These are the three critical points, the places where the derivative is 0. The horizontal tangents prove it, but which are peaks and which are valleys? We look at the second derivative. If the second derivative is positive, the point is a valley. If it is negative, it's a peak, because the second derivative tells us the direction of curvature. In the green regions, the derivative is positive and the function increases. In the red regions, the derivative is negative and the function decreases. Now we move into 3 dimensions, the x-axis, the y-axis, and the z-axis. This surface is the function x squared plus y squared, a bowl-shaped surface. The height at each point depends on both x and y. Let's look from different angles. How do we measure slope at every point on this surface? In one variable, we used a tangent line. Here, we use slices. I fix y equals 1. The plane cuts the surface and produces a curve. On that curve, we can draw a tangent. The slope of that tangent gives the partial derivative with respect to x. This symbol means the partial derivative of f with respect to x. The tangent moves along the slice. On the left, the slope is negative, in the middle, it's 0, and on the right, it's positive, just like before, but only in the x direction. Now let's look in the other direction. I fix x equals 1. The slice in the y direction appears. I draw the tangent. This gives the partial derivative with respect to y. The same idea, but now we move in the y direction. The slope changes again. What happens if we combine these two partial derivatives? At a single point, we draw both the x slice and the y slice. The two curves intersect at right angles, and the two tangent lines determine a plane. This is the tangent plane. In one variable, we had a tangent line. In 2 variables, we have a tangent plane. Look how perfectly it sits on the surface. It's the best flat approximation of the surface at that point. And if we write the two partial derivatives as a vector, we obtain the gradient vector, nabla f. One component is the partial derivative with respect to x, the other is the partial derivative with respect to y. This vector shows the direction of steepest ascent at that point. Now look again at the paraboloid surface. The lowest point is at the center and the surface rises outward. From above, we see circles. These are contour lines, points of equal height, like elevation lines on a map. Inner circles are lower, outer circles are higher. When the circles are close together, the slope is steep. And here are the gradient vectors. At every point, an arrow. Each arrow points in the direction of steepest ascent. Because the surface rises outward, the gradient always points uphill. From above, you can see that the gradient vectors are perpendicular to the contours. This is not a coincidence. The gradient is always perpendicular to contours. Pick a point. The gradient vector at that point is the red arrow in the xy plane. This arrow shows the direction of steepest ascent. If you were a climber on this surface and wanted to reach the top as quickly as possible, this is the direction you would walk. Walking in the direction of the gradient. Look, we are climbing along the steepest path. At every step, we follow the gradient. And what if we move in the opposite direction? The steepest descent. This idea is exactly what the algorithm called gradient descent uses in machine learning. Computers learn using this method. Red arrows point upward, blue arrows downward. The gradient tells the entire story of the surface, where to climb, where to descend, and where to stop. Nabla f, just 2 numbers forming a vector, but those 2 numbers contain the secrets of the entire surface. Partial derivatives alone give information about slices, but together they form a complete map of directions. And that is where the story of the derivative ends.